All right, so today marks basically the halfway point in the course, and we're going to switch our focus over to data structures and algorithms. It's a little bit more, it's still going to be practical stuff, but it's also a little bit more theoretical stuff because we're going to get into algorithms and algorithm analysis. So the first data structure that we're going to look at is lists, right? And you've been using these up till now without a second thought. A list of integers or a list of strings, right? And usually we've done an array-based, or array list-based implementation. Before we do that, though, let's go ahead and motivate this idea. The motivation is that we're going to have the dynamic data structures, as we've already seen, say lists, sets, maps, are way better than simple arrays, right? Because you can add stuff to them and it automatically grows. With sets, duplicates are not allowed and they're automatically checked. With maps, you can map an arbitrary element to an arbitrary element, right? So there's lots of additional features that come with these things. And of course it leverages OOP principles, right? Such as encapsulation, abstraction, and even polymorphism. Why? Because there's not one list for integers and another list for doubles, another list for strings, right? There's one list that you parameterize, and then you only need one implementation and one implementation only. And the reason for this, or the reason that we don't like arrays is because they are really, really limited. Oops, sorry. All right. So for example, let's come over here to our demo, and if I create, say, an array of, say, 10 integers, I'll go ahead and call it integer, all right? And I'll call it ARR here for short. And I can create a new integer array of size n, right? Now, what's the problem with this array, right? It's only of size 10, right? If I want to put in 20 things or 11 things or something like that, then that means that I'm out of luck, right? It's not going to hold more than 10 elements. What if I only have 5 things in there, right? Then, I'm wasting effectively half of the array. What if I wanted to insert something, right? I'm going to have to make sure that I move everything over and put it wherever it needs to be. And also, I need to make sure that it's not falling off, that it's big enough in order to hold it, right? So a lot of these things are solved by creating a dynamic data structure like a list. And that's what we're going to focus on here today. Again, there we go. So once created, the size is fixed, right? It does not grow, it does not shrink. And maybe you do want it to shrink because, of course, if it's of size 1,000, but you're only putting 10 elements in it, right? You're wasting a lot of space. So the solution is to use a dynamic list data structure. And the features of this are going to be that it allows you to grow, or automatically, I should say, right? Automatically grows, shrinks with new elements, right? New elements being inserted, or if you take elements out and it gets too small, right? You can add elements without worrying about the details, right? So if I add something on the end, I need to make sure that it's big enough to hold it. And if I add something in the middle, I need to make sure to shift stuff down. All those details will be taken care of by the class itself, right? This is basically abstraction. How does it add this element to the list? Who cares, right? That's the list's problem, not our problem, right? Now when you actually implement the list, then of course it becomes our problem. So we're going to go ahead and go with a demonstration here, right? Create your own array-based list. We'll want a way to add things, right? Maybe we want a way to remove things, right? A way to retrieve things, and maybe a way to modify elements in the list. Sound familiar? 4 things. A way to put stuff in, take stuff out, replace stuff, right? Remove stuff, right? CRUD, right? create, retrieve, update, and destroy. And that's why we call it CRUD with respect to databases, is because that's what it is, right? Those are the 4 basic things that you can do with a bag of things, or a collection, or a table in a database. So let me come over here, and let's go ahead and start. So I'm going to go ahead and create a new class here, and I'm going to call it my array, my integer list. There we go. Initially, we're going to just hold integers. Then we'll go ahead and abstract this away so that using polymorphism, so that we're not just it's not just good for integers. What should our integer? Now again, in practice, you don't write this, but I'm showing you how to write this because we need to understand the data structure. In practice, you don't do this. You just use a list and an array list implementation. What should our list look like, though? How would we go about doing this? So I need a way to hold stuff, right? So what should I do? An integer array, right? There we go. And I'll make it private. It's an array-based list, right? So it's my integer array list, if you want to call it that, right? To make it a little bit more specific. Let's go ahead and rename that compiled unit there, all right? So it's going to hold stuff in that array, right? We're not going to get away from that. That's how stuff is stored in a computer. But we're going to abstract away the details by encapsulating it in this class that is responsible for handling everything, right? Okay. We'll want to come back and maybe add some other stuff here. I need a constructor. So let's go ahead and create a public my integer array list. There we go. A no argument default constructor. One will be provided for you, but of course that means that this is going to end up being what value? Null, undefined. All right, so you want to create a list. Is there anything in that list to begin with? No. No. So how should we initialize our array? New integer of size what? How many things are in there? 0. We could do that. But well, you definitely can't do this, right? Because it requires an actual number here, right? It's kind of useless though to have an array of size 0. You can't put anything in it, right? So let's go ahead and bump that up to 10. Now, does that mean that there are 10 things in that array? No. It just means that it has a capacity of 10. Right? That means that I'm going to have an array that looks like this. This is not enough. 1, 2, 3, 4, 5, 6, 7. So let me go ahead and add a few more here. Oops. 8, 9, 10. There we go. Right? So 0, 1, 2, 3, 4, 5, 6, 7, 8. And then I'll tack on 9 over here to actually get 10, right? So is there anything in that array right now? No. So what would you say the size of the array is? Well, something is certainly 10. We'll give that a different name though. What is the size? Well, you just told me what's in there right now. Nothing, right? What's the value of nothing? 0. So what is another word for 10 here where we can actually hold 10 things? Here's a box that we can put 10 things into, right? It can hold that much. We call that capacity. It's able to hold 10 things right now, but it's holding 0 things, right? Why 10? Why, okay. 42. It doesn't matter, right? I'm just doing 10 for a number here. It's a nice number, right? Eventually we'll understand that you can actually tune this number and because you're going to grow and shrink it, right? And you're going to grow and shrink it by, say, a factor of 10 or a factor of 2 or something like that, right? 10 is just our starting point. I'm also going to want to keep track of the size of this, right? Because the capacity is built in. How do I know the capacity? The capacity is going to be this.array.length, right? That's the capacity of that array that I've got, okay? So I don't need to store that, but I do need to store the size, okay? Now the size in this case is going to be what? If I'm creating a brand new list and there is nothing in it, what is the size? 0. There we go. All right. Great. You may want to add a getter, setter, something like here. Let's hold off on that, okay? Now let's go ahead and think about using this from the outside world here. I want to create a myIntegerArray list, right? I'll call it numbers, is equal to new myIntegerArray list. There we go. Now, do I have anything that I can use on this now? Numbers dot say add or remove or anything like that? Nope. Why? Because I do not have any methods yet other than that default no argument constructor that simply initializes an array that looks like this with a capacity of 10. We can hold up to 10 elements into it and then a size of 0. So my first thought is I probably want a way to add stuff to this list. Public void, say, add element. And we're going to go ahead and take an integer, x here. Now let's describe, before we actually implement this, this method here, let's describe what we want it to be. Adds the given value x to the ... list. But how? Or where? So if you had a list here, an array with nothing in it, and you wanted to just add it, where would you put it? Okay, I agree. I would put it right here. So let's say that we're going to add 42 here. Okay? Now it's ... Suppose that you eventually have an array that looks something like this. There's 42, 101, 87, ... Right, and then there's nothing, right? Here the size ends up being 3. The capacity is still 10. We'll worry about that later. If you just said add an element to this list, where would it go? Where would you want it to go? Okay. So in other words, add means add to the end. Right? I agree. Right? Maybe you do. Right? Maybe you don't. Right? We'll talk about that in a second here. So it adds a given value x to the end of the list. There we go. Help me out. How do I implement that? If there's nothing in there to begin with, the size is 0. So where you told me where do you want to add it? At index 0? Right? So if size is 0, then this dot array sub 0 is equal to x. All right, that's a good start. What if the size is 3, like in our example over here? Where do you want to add the, what index do you want to add it at? 0, 1, 2, 3. Right? Okay, so if the size is 3, right, this dot array sub 3 is equal to x. Do we start seeing a pattern here? Exactly, so, because I want to establish a pattern, right? Now, go ahead and suggest an improvement here. Okay, so this dot array of this dot size is equal to x. There. Good. Once if I've got 3 things in there and I put a 4th thing in there, what is the size now? 4. This dot size plus plus. I like that. Okay, so let's come over here and add a bunch of things to it. Numbers.add 10, numbers.add 20, here I'll go 42, 10, 20, 30. Right, there we go. Let's run it and see if it works. Oh, okay. How do I know it works? Silence. Okay, silence is golden, right? How do I know that that stuff got in there? Okay, so let's do that next. You could print it in poor man's debugging, printing, or I could go ahead and do, and we are going to want that, but I could go ahead and set a breakpoint here, right? Switch over to my debugging perspective, rip open my class here, and look at the array and its configuration, 42, 10, 20, and then as I step through this, there we go, 42, 10, 20, and 30. What about the rest of that stuff? Undefined, null. And the size is 4. So it looks like everything is working. I'm not going to want to do this every single time. So I agree. Let's go ahead and add a method to print it out. Ideas? ToString, exactly. ToString. Right? Terminate. I was still running the debugger there, right? All right, so I could go ahead and go into a for loop. For int I equals 0, I is less than this dot array dot length, I plus plus. Let's see what happens here. Yeah, I'll have a string. String s is equal to what an opening square bracket here. And then I'll go ahead and say s plus equals, what is it going to be? This dot array of I plus a comma, right? And then at the end, s plus equals that closing bracket right there. There we go. And then I'll go, of course, I'll say return s. Let's see if that works over here. System.out.println numbers. All right, well, first of all, it's getting everything. Why? Because I was iterating over this and using the capacity instead of the actual size. So let's change this. This dot size. I like that. Let's run it again. Okay, now we're only getting those things. We've got a superfluous comma here, and in fact, I don't like this at all. There's got to be a better way. Somebody's already done this, right? Arrays dot ToString of this dot array. And I'll return this. Except that when I do that and try to cut a corner, what's going to end up happening? It's going to think in terms of the capacity instead of the string. So maybe I do want this because there's nothing built in that's going to do that for me, right? Oops, come on, undo. There we go. How could we take care of that superfluous comma? Do we really care about it? Okay, and then will this work? It only gives me 42, 10, 20.
Do one before you start the for loop.
Okay, I could take care of it before the for loop, or I could take care of it after the for loop, right? S plus equals this dot array dot of what? This dot size minus 1. There we go. I like a little bit of spacing around this, so let's go ahead and do that. And that looks good. Always rigorously test your code. There are always going to be corner cases or edge cases where something goes wrong. For example, what if I printed this out before anything was even in there? Let's find out. Uh-oh, index -1 out of bounds. Why? Yep, I'm taking care of that last one when I shouldn't be taking care of that last one. We could do a string builder, or we could just take care of this corner case separately, right? Special cases require special code. If this dot size is equal to 0, then I'm going to return a special string, empty, right? Indicating that it is in fact empty. But now, once I've added 4 things to it, it's no longer empty. Right? So if you've got corner cases, you may need corner case code to take care of it. All right, let's keep going. Corner. Exactly. For int I equals 10, I is less than or equal to 100, I plus equals 10. I'm going to add numbers dot add I. There we go. I'm going to add 10, 20, 30, 40, 50, 60. All the way up to and including 100. Yeah, do we have enough space for that? No. Once we've filled it up, right, let me go ahead and go up to there. Right? Once we've filled it up, it's perfectly fine, right? But once we add that next element, say 100, that's when we get into trouble. How do we take care of this? We need a bigger boat, right?
It looks like we ran into a problem we can't solve. Guess we're gonna have to go home now.
We could. We're a little bit ahead. All right. So, ideas. If the array is too full, ... what should I do? Make a bigger boat, right? If the boat's too small, you get a bigger boat. So if the array is too full, or is full, right? There's no too full. right? If the array is full, then what should I do? Oh, first of all, how do I check for that? If this dot array,
Size equals capacity.
this dot size is equal to this dot array dot length, which is our placeholder for capacity, we know that it's full. Right? All right, let's come over here and think about that. What if it is full? I've got 42, 10, 20, 3, 4, 5, 6, 7, 8, 9. I don't want to write too much. I want to tack on 10 over here though. So what do I need to do?
Staple on and then
Yep, I need a bigger array. So let's make a bigger array. Integer array, or new, I'll call it BRR for new array, ARR, BRR, right? Is equal to new integer array. How big should it be? At least as big as the old one, right? Here it is, there's our capacity, plus 10, okay. And why 10? It's just a number, right? If you want to, change it to 1. If you want to, change it to 100, right? You can tune that number later on and see what works best.
So wouldn't, wouldn't like, this would probably be a more processor intense thing to do, is just like constantly replace arrays, so you want the number to be bigger just for efficiency?
You could, in fact, you could make it adaptive. So, in fact, this is what TCP/IP does, if you have any networking background, where we send a successful packet of size X. Great, we've got a good network connection. Go ahead and double it next time. 2X. Great, we still went through. Still keep going, right? An exponential increase in the size of packets until we hit a brick wall. And then we lose packets because we're sending too much information. At that point, we pull it back, but we don't pull it back exponentially. We pull it back linearly, right? So some constant factor there where we go down. So increase because you want a quick increase, right, until you hit that capacity, and then you want to pull it back, but you don't want to jump all the way down. So you only gradually come down. And there are schemes like that all over the place that have been developed by empirical research of, well, this scheme works best, right? And so you could go ahead and say, double it. Right? You could go ahead and say, go up a more order of magnitude. That's probably too much, right? I'm just going to go ahead and go up incrementally, linearly. Right? Keep it simple for now.
just square the size of the length.
You could go up quadratically, yeah. This dot length times this dot array dot length, right? There's quadratically right there if you want to. I'm going to keep it simple for now because the point of this is not to empirically test this thing for efficiency. The point is to let's get it done, right? All right, so we've got a new array. I can just make this dot array point to that now, right? No? Why not?
That's not how pointers work.
Well, I could. All right. There we go. What happens? It's of size 20. It's of size 11 now, right? It's of capacity 20. But what happened to everything that was in there before? It's all gone, right? Why? Because BRR was just initialized to a bunch of nulls. So I want to copy over the other elements, dot, dot, dot. So for int I equals 0, I is less than this dot size, I plus plus. Right? You've seen this before. We did this in C, right? This is a deep copy, right? For int I equals 0, what's wrong? Oh, I didn't type I. There we go. BRR sub I is equal to ARR sub I. There we go. And then I can make the new array, this array point to that new array that I just created. What about the old array, by the way? If this were C, what would I have to do to it? Free it up, clean it up, right? Do I have that worry in Java? No, because of automated garbage collection. There we go. I can keep going, right? I could do this for a long time, right? I could go ahead and add arbitrary number of elements to this, and it will never be enough because I'm always increasing the capacity as I go along. Right? bump that down though. There we go. Okay. In fact, all this stuff here, I had to write this in C because C didn't really give me much to work with, other than I could do a memcpy, so I could get this down to 2 lines of code. But in Java, it's better. Don't write that. This dot array is equal to arrays dot copy of. Look at all those copy ofs, right? Those are all deep copies of integer arrays, double arrays, character arrays, whatever you want. I want this copy right here. Right, of the old one, this dot arr. And now there's another value over here, right? And this is going to be this dot array dot length plus 10. It's a really cool implementation because if you read about it, copies the specified array truncating or padding with nulls if necessary, so that the copy has the specified length. For all indices that are valid on both the original, in other words, if you say I want to copy this array of size 5, but I want to copy it with a new capacity of 10, it'll copy over the first 5 elements and then pad it out with a bunch of nulls or zeros. Right? So this does exactly what we were doing before, and I have exactly the same behavior. But I've done it in 1 line of code instead of rolling my own solution. Right? Okay, this is great. Right? So we have a way to add things. Maybe we want a way to remove things, a way to retrieve things, a way to modify things. Let's go ahead and focus on this third one first. Okay? I want a way to retrieve things. Well, I can always print them out, right? And that's what I'm doing right now. So that's kind of retrieving. That's not enough. What if I want the third element, dot, dot, dot. So an element at index what?
2.
So get element, or let's say numbers dot get element at index 2. I like that. So let's implement that. Right. In fact, does it let me add that? Yeah, create method, yeah, okay. It'll at least stub it out for us. Of course, it doesn't do anything yet. All right, so how would I do that in terms of the array? Return this dot array at index I. All good, right? Now let's go ahead and print it out to make sure that it works. There we go. 20. Okay. That's the third element, right? We're good. What about the 20th element? Does not exist. So, oh, here, let's go try this first. What about the 15th element? There are only 11 things in there, right? So, does not exist, but in a way it does. Oops. Save. Sorry, save. There we go. There. You are getting a value, but it's null. Why? Because there's 42, 10 through 100, and what else is over here that we're not seeing because we're skipping it? A bunch of nulls.
If you make it a capital integer, could it have it null?
It will, and then it will actually print it out as null. Oops. No, why not?
Well, that might be another one.
Oh. Change this to, actually I'm going to do this anyway, because it's exactly what I want later on. There we go. Now it's going to print out null, right? What about 20? Now I'm going to get an index out of bounds exception. So, giving me some things to think about here as far as how I should implement this, right?
You probably should make sure that the thing exists.
All right, so how can I do that? If you ask me for an index, what is an invalid index?
If
Anything larger than
index
Okay,
is
if this
out of bounds or points to null.
this dot array dot length. All right, so if the index is greater than the capacity, I agree with that. But remember that the index was not greater than the capacity over here when I had it at 15. That certainly qualifies right there. But 15, is there a 15th or 16th element here?
Not really.
So I don't want to make sure that it's correct with respect to just the capacity, but if there are only 10 elements in there, should you be asking for an element at index 10? Even if it's of size 100? or of capacity 100. No. This dot size, okay. Think about that. There are 5 elements, 0, 1, 2, 3, 4. So you should not be asking for anything greater than or equal to size. Think about the other direction. There's nothing stopping me from asking for the negative 15th element. Should we allow that or not? No? Okay, I agree, because this is Java. That's weird, right? So if index is less than 0 or it exceeds the size, then we will go ahead and error handle here. Now, in a programming language like Python, negative indices are perfectly fine. Why? What happens? It wraps around to the beginning, right? Maybe that's the behavior that you want. It's not the behavior I want because this is Java, not Python.
Yeah,
Question?
it's an array, not a graph.
Exactly. Or in Python, they still call them lists, and so they have the feature that you can go back, wrap around to the list. All right, so how should we error handle this? Return null. We could. In other words, silently handle this and say, you asked for something that doesn't exist, here you go. No, nothing. No. What's another alternative?
Does not exist.
Okay, so system.out.println does not exist. And then move on with our lives. Return, we still have to return something. Return null. Oops, index. There we go. So, does not exist. Does the array list implementation do that? Probably not. Why? Because nobody's sitting there staring at the system.out. In fact, one of your bonus items for not for this phase, but for the next phase when you're doing JDBC, is to get rid of system.out or system.error entirely and to use a proper logging system. Log4j is what we suggest. When we get closer to that phase, I'll go ahead and show it to you if you want. Otherwise, I've got video. I'll just point to a video or something. Right? You don't want to do this because nobody is sitting there staring at the screen waiting for something to happen, for a message to come across and say, oops, we have a does not exist exception, a problem. I'll go ahead and jump right into the code. Right? So how should we handle this? How does Java handle error handling? Throw, new, runtime, runtime, exception. There we go. Rum's gross. Runtime exception, invalid index. Plus index. There we go. Now over here in my demo, exception, invalid index 15, negative 15. Okay. Invalid index 15 because it has a size of 11, right? You can report all that information if you want, but we throw an exception at you. And we make sure that it's an unchecked exception so that you're not forced to surround it with a try-catch. Excellent.
Is that how it's different than what it was doing before?
Yeah, what it was doing before was just saying, sorry, I can't do that, and then giving you null. Right? It would have been return null. And now get rid of this. And what I was doing before was, there it is, null. All right, well, how do I know that I shouldn't have asked for that? I want the 15th or the 16th element here. How do I know that I shouldn't do that? How do I know how many elements are in there?
Should check sign.
Yeah, if numbers.size is greater than or less than or equal to 16, then I'll go ahead and get the 16th element or whatever. Yep, I don't have that, do I? So let's go ahead and give that to me, right? Again, it's your class. You can do with it what you want. Public int get size is what I'll call it. Return this dot size. Okay, excellent. Now I'm not going to use this. I'm just going to go ahead and make sure that it works. System.out.println numbers.get size. There. And the size should be 11 because I put 11 things in there. Okay? Oh, you know what? What's good for the goose is good for the gander. Let's go ahead and go with public int get capacity. Right? Return this dot array dot length. Does that sound like a good idea? Let's come over here to the demo, and let's say if numbers.getCapacity is equal to numbers.getSize, right? Then to do, you need to increase the size of the list. It already does that, right? That's the whole point of abstraction. Why do we, capacity, what the hell is capacity? This is a list. I put stuff in, I take stuff out, right? It takes care of all those details for me. This is called a leaky abstraction because I am exposing part of my internal workings of the class to the outside world, saying, you know what, I've got an array in there and it's got a capacity, and you know, why are you telling me this? You're the list, you take care of it, right? I'm not going to have a leaky abstraction here, right? I'm not even aware that it is going to be an array under the hood. It's just a list. This is why we have list and an array list, a list, and eventually we'll talk about linked lists, right? It's just a list. A list is a list is a list. Yeah.
You mean it's all just
Yeah, an array list, we'll take a look at it.
Obviously, yeah.
I'm recreating an array list implementation here, right,
Yeah.
without all the bells and whistles, right? So let's go ahead and make sure that we're documenting this. Retrieves the element at the given code index, right? Throws an exception for any invalid indices, right? There, we've documented it, right? It's going to throw it back at you if you ask for something that doesn't exist. Returns the current size of this. Go ahead and do, I'll put in a to-do documentation, right? Otherwise you'll lose those small little points. Okay? Well, we've got a good start.
Do we need to document the getter?
Probably not that, well, that one, yes, because it's not a, I guess, yeah, that's a non-trivial one. The size, it returns the current size of the list because it's dynamic. It's mutable. It can change. It can grow and shrink, right? Before we go on, I want another way to add things, right? So I'm going to come back up here, and what I want to do now is I want to add, say, 42, but I don't want to add it at the end. I want to add it somewhere in the middle, right? So add element somewhere in the middle.
Insert
There.
element.
Okay, I like that because that's what you're doing. Insert element. Now,
That's
somewhere in the middle.
No, that doesn't quite seem like.
Yeah, you need a little bit more specificity there. So insert element 42 where? Okay, at index, say 5. Insert element at index. I like that. Let's go ahead and create a method to do that. At element int x at index. There we go. And I'm going the same direction there. There's my element, there's the index. So my English is insert element at index. Insert at index, probably go the opposite or something like that. All right. Can I just do this? This dot array of index is equal to x. There we go. That'll work. Let's print it out before and after. There we go. There it is, 42. Did you mean to delete 60?
Depends on what your definition of insert is.
Yeah, so insert, that tells me it's kind of like replace element at index, right? That's not what I wanted. Maybe that is what you want. Go ahead and write that function on your own. I want to insert the element at that particular index. Okay, without having to delete the other one. So I've got now, say, 5 elements in here, and you want to insert it right here. Right? What do you need to do? Shove these guys over so that you can put them right there. Right? So, to do, move elements from index to size -1 down. In fact, I'm gonna call it something else. Shift elements from index size to index to size -1 down or over to make room. All right? Then you can put it in. Suggestions on how to do that. I could do a for loop. For int I, I'm not going to start at 0. I'm going to start at index. I is less than this dot size, I plus plus. That'll certainly go from index to index plus 1, index plus 2, dot, 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 all the way out and down to the last one. Right? Move element ARR I to ARR of I plus 1.
So you need to make a copy.
Okay, so int copy array of I plus 1. And now I'm free to move it over, right? So array of I plus 1.
I mean a copy of the array.
Well, I don't know that we need to make a whole copy of it, right? If it's capacity, we'll come back to that idea. If it's full, certainly we do. But if we've got room over here, we can just shift stuff down. Right? And we do have room here because there are only 11 elements in there. We know that the capacity is 20. We can just go ahead and shove stuff down. This is going to be equal to ARR sub I. And then what do we do with the copy? ARR sub I plus 2 is equal to the copy. Okay.
Shouldn't you start at the end?
Okay, that's a good idea. How about instead, because if we're moving this guy over, then that means that this guy has to be moved over. That means that this guy has to be moved over, moved over, moved over, moved over. It's much easier to just start at the end and move this guy over, then this guy over, then this guy over, then this guy over, then this guy over. So let's go ahead and start at the end, which would be this dot, dot size minus 1, right? There are 5 elements in there, 0, 1, 2, 3, 4. I want to move 4 over to 4 plus 1. So move element ARR sub I to ARR sub I plus 1. So ARR sub I plus 1 is equal to ARR sub I. There we go.
Shouldn't you make it like decrements instead of increments?
Okay, good. Because we're going to start at the end and work our way over. Now, what else do we need to put in here? Where do we stop?
Greater than. Oh,
Good. Greater than.
Size minus the next one.
Well, so if I'm going to go backwards, originally I was going to go index up to size. Now I'm going to go from size minus 1 down to index. So greater than or equal to index. There we go. Let's see if that worked. Uh-oh. Yep. Oh, am I not inserting? Where am I inserting it? Thought I had done it after. 42. Uh-oh. All right, so this dot size minus, it shouldn't be that big. This dot size minus 1, well, it's greater than index I minus minus. This looks good. Oh, did I not insert 11 things? Oh, because I took out 42. So it's, sorry. Let's go ahead and go up to and including 110. There we go. All right, so there, this will work now, and then we'll come back and fix what we were thinking about here, okay? So 10, 20, 30, 40, 50. Now I'm not deleting 60 anymore. 42 is right here. 60, 70, 80, 90, 100. Ooh, what are we missing now? 110. Let's come back over here and think about it. I'll tell you that this successfully shifts everything down. This successfully inserts that element. But if you're going to insert a new element, what happens to your size?
It goes up by 1.
Okay, so size plus plus. There we go. Run that. There we go. So there, it was just missing because we didn't have that that size. And of course now it's 12 because we've got the original 11 elements in there. 42 is right in the middle. By the way, was it correct? 0, 1, 2, 3, 4, 5. There we go. So it looks okay to me. Again, corner case tests. Let's add 42, not to element 5, but to say 0. Where would you expect that to be now?
Instead of the 10.
Instead, so yeah, okay, so we're going to insert it before the 10 here. I agree. Right. What else should we test? What if you add it to the 10th index? There we go. That's what I would expect it to be. What about the 11th index? Where would you expect it to be? At the very end. Works as well. If you inserted it at the 12th index, where would you expect it to be? Ugh. So, there's null, and then there, after that, there's 42. Back to the drawing board. What is a valid index with respect to insert? If index, well, first of all, if it's less than 0, should we accept that? No. Or index is greater than or equal to this dot size, is that valid or not? I'm going to go ahead and just steal this.
Equal to should be okay. Just
Okay, I agree. Why should it be equal to is okay. If you've got 5 things in there and you want to insert at 0, 1, 2, 3, 4, all of that makes sense. If you want to put it at the end, that makes sense too, right?
I mean, you should just use the, I don't know, add element or something, but insert, I guess.
I like that idea. So for those that can't hear online, the suggestion was, wait a second, you've got a lot of repeated code here, right? That one, that one case is taken care of by this up here. Right? So I agree. One of these probably should be simplified to call the other. Let's think about this one. This one should call this one, or this one, or this one should call this one. Which one is more general?
Insert.
Insert is more general, I agree. So how would we say this dot insert at element at index? I want to insert X, but where do you want to insert it?
Size.
This dot size. There you go. Excellent. Now we have one function to worry about over here. What else do we need to worry about? This stuff, right? Repeated code here, I'm going to take care of that. There we go. Done. What happens when we get too full? We need to make sure that we've got capacity for it. There we go. Right? So if the index is off, then we'll go ahead and throw invalid here. Otherwise, if and by the way, did I keep the error handling up here? No, I did not. I should have, right? Because it's a different it's a different criteria up there. Let's see. Actually, no, there is no criteria to check here. You're just saying add it to the end, add it to the end, add it to the end. Right? There's no error handling there at all. So let's come back down here. If you're at capacity, then we simply copy everything over. Then we shift stuff down in the new copy. Then we insert it, and then we increase the size. Let's come over here and see if it works. Oops. Oh, well, that's invalid. Let's go ahead and add it at 11. Right, there we go. That works. And by the way, I've had to erase and add these back in, right? I'm doing ad hoc testing. Does this sound like a good idea? Does this sound repeatable as I'm going along? Right? It's a good idea to do this kind of stuff for a sanity check, right? But what would you want to do ultimately if this were a real implementation? JUnit, exactly. Right? You would want repeatable tests. What happens when we insert it at this index and that index and that index and that index and that index? Okay. For now, though, this is good enough. Okay. If I insert it at index -1, I should expect a exception being thrown. If I insert it at index 5, that should still work. 10, 20, 30, 40, 50, and 42, right? And that still works. Okay. All right. Want a way to remove things. What would that look like?
It's gonna need to be similar to our insert, but just remove it and it should.
Remove element. In fact, you could say remove the element at the end, right? But I'm going to end up calling this remove element at index, right? Int index. Right. So right now I'm saying void here. Is there another way that we could? We'll come back to that. Remove element at index. Let's go ahead and see if it works. Well, not yet, obviously. All right. But let's go ahead and have a test case here at least. Dot remove element at index. We'll go ahead and remove the thing right before it, right? That means that 0, 1, 2, 3, 4, we'll remove 50, okay? So we would expect 50 to be gone, but everything else would still be there. Right. Okay, remove element at index. That's gonna leave a gap, right? So, come over here. What are you gonna do to take care of that gap? What if I wanted to remove this guy right here? Right. Should I just leave it as a blank? No, I don't like that either. What are you gonna wanna do with the rest of this stuff? Shift it, shift it, shift it, shift it. Right, so, let's come back over here.
Start from when you delete.
Now, yep, if I delete this one, all I need to do is copy this one over. So, for int I equals index, I is less than this dot size, I plus plus. I will copy or shift down. So this dot array of I is equal to this dot arrays of I plus 1. Right, the one right next to it gets shifted over, shifted over, shifted over. Let's see if that works. Yeah. All right, well, 50 is certainly gone. But what about the tail end there? Null. There you go. Anytime you add something, you need to go size plus plus. Anytime you take something away, you need to go size minus minus. Yep. Or yeah, you could do this if you want to, but all right, that works. Let me come over here and show you. While numbers dot is not empty, right? Empty. Let's go ahead and remove stuff. Let's clear it out. Numbers dot remove element at index 0. Right, there we go. We'll just keep removing the first thing, the first thing, the first thing, the first thing. First of all, do I know if it's not empty? Nope. In terms of the size, get size is greater than 0. But wait a second, you know, I really like that term, while it's not empty. Maybe that's another piece of functionality that I can add over here. Public Boolean is empty. How do I know if it's empty? If size is equal to 0, it is empty. If size is not equal to 0, we know that it's not empty. All right? So numbers dot is empty while it's not empty. I will go ahead and remove elements. Let's see if this works and print it out at the end. Empty. Right? What if I go one more? If it's already empty, can you remove an element at that index? Let's find out. Oh, it worked. Uh-oh. Yeah. Oh, that finally it finally errors out here. Why? Because my size went down to -1, -2, -3. Let's come back here and think about a corner case. If it's already empty, can you remove that element at that index? No. In fact, we should check that index as well. Right? If the index is less than 0, or the index is greater than or equal to the size, then those are definitely, this dot size, those are definitely bad indices to be removing from. So throw new runtime exception, invalid index plus index. There we go. Doesn't solve our problem though of well, I guess it does. Right? If you ask her if the size is 0, then any positive or 0 index here will end up being an invalid index, right? You could change this so that if it's already empty, if this dot is empty, you ask me to remove anything at all, I'll go ahead and throw a new runtime exception with a different message. list is already empty. There we go. And I get list is already empty instead. You could have, in fact, changed this so that they're not two runtime exceptions. Instead, they're very, very specific exceptions. List is empty exception and index out of bounds exception. Right? You could combine them in some way too if you wanted to. Otherwise, it's pretty good. It's actually going to work because it's now down to empty. Okay? That's a way to remove things. In fact, let's come back over here and implement that remove from end to now. Right? There's add element to the end, public void remove last element. There we go. This dot remove element at index should be what? This dot size. There's one thing in it though. Where's what are you trying to remove there?
Oh, minus one.
-1. There we go. Always off by 1. Right. I like that. So far we have at least 2 ways of adding things. We have at least 2 ways of removing things. We have at least 1 way of retrieving things by index. Right? Now let's go ahead and maybe a way to modify elements. We already did that though. Right? If you're willing to replace an element, in fact, let's do it, I guess. Get element at index, remove element at index. Let's go ahead and go with public void replace element at index int x. Then
Could you, this is probably pretty generic, but could you like add an index and then just remove the index?
you could think about what you're doing. So you're shifting all this stuff up just to shift it back down again.
Right.
Now thinking that we're eventually going to do this, but think about in terms of very large lists, 1 million things, and you want to add one over here. 1 million things being shifted, 1 million things being shifted. That starts to get, inefficient. Right? So let's just go ahead and replace the element at that index. Let's see. Invalid index, replace element. I do need an index, right? There we go. Int index. So there's the element that we want to replace it with. There's the index. So if the index is negative or if the index exceeds the size 0, 1, 2, 3, 4, -1. Yes, that's right. Invalid index. And then this dot array of index is equal to x. Do I need to increment the size, decrement the size if I'm replacing something? Nope. Right. That's got me thinking about this void function here. So how could we make this a little bit more flexible? You give me x and you want to replace y over there. I go, okay, I'll go ahead and take x. What do I do with y? I'm just throwing it away. What else could I do? I could return it. Right? Int y is equal to this dot array sub index. Then replace it and then return y. Right? Let's call it temp instead so that we're not confusing these things.
And you could still call that without doing like in the main, like in something, and it would just disregard
Exactly.
y.
You could, so you could do something like this. Numbers dot replace element at index. Let's go with 7 and we'll replace it with 101 and then print it out again.
You get that back.
Oops, did I? Oh, you're right. Replace it with 101 at index 7. Be consistent about that stuff. So there's 101. And then we ultimately didn't grab it, but we could have. Int foo is equal to, and then print out foo. Same behavior. That gets me thinking about, well, if you remove element at index, maybe you also want to return it. Right. So before we shift it down, let's go ahead and grab it. Int temp is equal to, the thing that we're going to remove is at index, so array of index. There we go. After we've shifted everything down, we've essentially deleted it, return temp. There we go. Still works. Right. So we've got the same basic 4 things here. But what good is our list? It's in the name. My integer array list. What does it hold? Integers. Okay. Now I need to do this for doubles. Copy, paste. My integer, my double. Oh, well, let's just do it with strings. String list. There we go. And let's open that up and see how I shouldn't. My string, my array string list. My string. This is why we don't name it like this. String array list. There we go. Rename this. There we go. All right. So what does it look like now? String array instead. String array instead. So add element. Now that's a string. Remove element. String, string. Get element returns a string. Index is still there. And then this is a string. And then this is a string. This returns a string. This returns a string. That's a string. Good. What else? And then X needs to be a string. There we go. That's all of them? There we go. What did I do? Did I change any code? Did I really make any changes to the code? No. Nope. Let's go, in fact, go ahead and compare them with each other. Right. Is there really any difference between any of these other than integers become strings? Integers become strings? Integers become strings? No. Nope. Every single line of code is exactly the same. So copy paste every single time I want something like this? No. Copy paste my array list. There we go. And let's open that up and let's clean it up. So you're right. What should I do? Parameterize this. Right? It's not integers, it's what? T. It's an array of T's. It's not an array of integers, it's an array of T's. We'll come back to this here in a second because you can't do that. All right. You're not returning an integer, you're returning an element of type T. You're not taking an integer, you're taking an element of type T and returning an element of type T. T. You are not returning an element of type T, you are returning, you're returning an element of type T, not an integer. Right? And what else? Insert at element, there we go, T at index. There. Everything's taken care of now except for these two lines up here. Oops. T. There we go. Right. I did the same exact thing, but instead of replacing integer with string, I replaced it with this generic T. Right. Now this is one list to rule them all. Right. I can put integers in here, I can put strings in here, I can put whatever I want in here. And I only need one implementation. I can go ahead and remove all these implementations over here. The one problem here remaining is this line right here. When you call the new keyword, think about it in terms of C now. When you create an integer array of size 10, how many bytes do you want? 10 elements, but each integer takes how many bytes? 4, right? 4-byte integer. So you want 40 bytes. What about a double? 8 each, so now you want 80 bytes. How many bytes does T take? It could take 4 bytes, it could take 1 byte if it's a single byte. It could take 8 bytes, it could take, I have no idea. So what we're gonna have to do is we're going to have to use a raw type here. An object takes elements, is nothing more than a reference. And references, I believe, are always 8 bytes. Right? So I still need to force this to become an array of objects of elements of type T. This is because of parameters being introduced in Java 4 or 5 or whatever it was. Right? In other words, we still need to be backwards compatible with Java 1. And so therefore, we need to use this raw object here. In fact, you can go ahead and suppress this unchecked exception here. This is an unchecked, you know, what do I want to call this? An unchecked typecast. That's it. That's what this is. This is a typecast right here, right? You can go ahead and put you know, suppress that warning there, but it's perfectly fine. Why? What if I created an array, my integer array list of say strings? My array list of strings. Names equals new my array list of string. Right, there we go. Names, excuse me. Names.add. Can I add an integer to it? No, why? Because of proper parameterization. You said that my array list is of elements, holds elements of type string. Add element here takes an element of type t, which you've already said is a string. So we're not going to allow you to do that. Consequently, it doesn't matter that you're using raw types up here because your interface protects you from it. Nobody can come in and add an arbitrary object to it as long as you have properly parameterized it like this. Right? I could create my array list of integers. Integer numbers 2 is equal to new, like that. And then numbers 2 dot add, I can add a 10 to it. Numbers 2 dot add element, I can't add hello. Why? Because it's properly parameterized
How would
here.
it behave if you do that, just error? What kind
It's not even going to compile, right? Because you said that this was a list of integers. You try to add something that's not an integer, no compile. Right? And that's how we achieve it over here, to be backwards compatible with Java 1 all the way back to 25 years ago. Right? It's perfectly fine because your interface does not allow arbitrary objects. It only allows objects of type T, and you parameterize them to objects of type T.
Yeah, it would probably be bad if you could just add one and
Yeah, then you'd be living 25 years ago with Java 1, 2, 3, right? Where you had no type safety at all. Everything was just this generic raw object. You could put strings and integers and doubles and whatever else you want in the same list. Most many programming languages are like that, by the way. A list in Python, you can put whatever you want into it, including another list. PHP, JavaScript, they have no strong typing, so you can do whatever you want, right? And it is chaos. Right? Better cross your fingers that whatever you pull out of there is exactly what you expect of it. Here, there's no crossing your fingers at all. You can't even do it.
there's C where you don't have a list.
Yeah, C is even worse, but yeah.
How would you make a list of lists here? Could you do like a myArray list?
Yeah,
See myArray list or something? Or
you
how would
could.
that go?
I mean, technically speaking,
This is like a kind of a two-dimensional kind of thing.
Sure, and like that would work?
Yeah.
No.
You need to bar, because I've already used foo. But yeah, you could do that. If you're thinking that you want to do matrices, though, look for a library or something like that. But yeah, because the reason that you wouldn't want to do it on this is because it's just a list of arrays. This array could be 5, this array could be 8, this array could be 3, this array could be 7. Right? That doesn't sound like a matrix to me. Right? A matrix is always going to have n by m dimensions. Right? But you can do that. You can parameterize whatever you want. Right?
technically speaking, a list of strings is two-dimensional. 'cause
Technically, yeah.
strings are an array of characters.
Technically, yes. Here, what's string x? What is it? It's a. Where's my? Come on, where is it? I've already passed it probably.
Yeah, that seems
Find
like that would be a
byte.
very long document.
Find byte. There it is. It's an array of bytes because it supports Unicode, not just characters, chars. In fact, again, you don't roll your own in real life. You use an array list. array list for integers, foo, or bar, because I've already used foo. There you go. So let's bring that in, and let's take a real quick look at what it looks like. Yep. An object array. Look familiar? That's exactly what we just did, right? And it looks like it initializes it to an empty array. Oh, there's the actual element data. And then, hey, they're keeping track of a size, right? And when you get to a capacity, it what? It increases the capacity, right?
By how much?
That's a good question. I'm not sure. Hey, look, it uses copy of, right? Just like we did. And it looks like the size. Ooh, I don't know what that's doing there. So
It's like an instance of thing.
size. So it copies. Trim. This trims, so it actually shrinks. Ensure capacity. Grow. There we go. That's what we wanted. Obviously, it's a private here. It's going to grow, and let's see. Ooh, minimum growth is going to be minimum capacity minus old capacity. Preferred growth is going to be. Oh, do you know what that is? That's a shift, a bit shift by right by 1 bit. So in other words, it's the equivalent to multiplying that by 2. It does increase exponentially. So if the capacity was 10 before, now it goes to 20. Then it goes to 40, 80, right, 160. That's the preferred growth.
I didn't realize Java had bit operators.
It does. It has bit operators left, and it also has cyclic bit shift operators. Int x is equal to, let's go with 1, and then x right shift. Is that what we want? Wait a second. That doesn't make any sense then. If it was a right shift or a left shift.
Well, one's division truncation hills.
Okay, so over 1 bit.
Much use for bit masks might have.
There we go. And then system.out.println. So what should that do, by the way?
Change it to 2.
It should multiply it by 2. Okay. Unresolved compilation issues.
Duplicate.
Oh, okay, fine. There we go. I said,
Undefined
what?
import heights.
What is, oh, it's because x is a string, damn it. There we go. Int x. There we go. Finally. There we go, 2. What if I initialized it to, I don't know, 64, and then I right shifted it by, say, 2.
32.
So 32, then again,
Oh,
16. There we go. So yes, you do have bit shifts. You have cyclic bit shifts.
Yes, we're talking about that.
There we go.
Wait. So that just.
Yeah, it's not going to do anything with this one because there's only one bit. But if you did it, let's go ahead and take this down to 4. So 1, that should still be 1. But if you do it one more time, then it should be, that cyclic is going to come around and make it a negative, so that I imagine this is going to be -0. Yeah, something like that. Let's go one more. Shift it over to, oh,
Yeah,
okay.
that's why I was surprised to see.
It's not cyclic. It's not cyclic apparently. It's just it's dropping it off maybe. I'm not sure. But anyway, so you're doing bit you're doing bit twiddling. Do you use that term?
Working in assembly,